Okay, in section 1.1 we looked at degree measure, so it's just a unit of measure that we can use to measure angles. In section 1.2 we'll look at radians. So there's just a conversion between degrees and radians, just like the conversion between inches and feet, or feet and yards, something like that. So the conversion, 180 degrees is equal to 1 pi. So pi radians. Now, with degree measure, we use this little degree circle. I wrote radians here so you knew what I was talking about, but whenever we're describing radian measure or using radian measure, we don't ever actually write the unit. So if there's just a number or a pi or something like that, then you know that we are in radian measure. You've probably seen pi before. Pi is approximately 3.14. Again, I'm going to write it just so you know what I'm talking about, but we usually don't. So pi is approximately 3.14 radians. But this is the conversion that we'll use to go back and forth between degrees and radians. So to go from degrees to radians, I'm wanting radians, so radians will be on top. So whatever our original degree measure is, let's say I want to convert 30 degrees to radians, let's say that. Then I'm going to multiply my original angle, so in this case 30 degrees, times, I want radians, so I'm going to put radians on top, so pi over 180 degrees. So this is going to be, I'm multiplying fractions, so straight across I get 30 degrees times pi over 180 degrees. Degrees cancel out. 30 over 180 simplifies. Pi stays on top. Over 6. Right? Zeros cancel out. 3 goes into 18 6 times, so pi over 6. So 30 degrees is equivalent to pi over 6 radians. So if I'm going from degrees to radians, I'll multiply my original angle in degree measure times the ratio pi over 180. If I want to go the opposite direction, let's say I'm already in radians and I want to go to degrees, then we'll just flip that ratio over. So let's say I want to go from pi over 4 to degrees. Then I'll take pi over 4 and multiply it times, again, the reciprocal of this ratio. So I'm going to degrees, so I want degrees on top. So 180 over pi. So again, multiplying straight across, I get 180 pi over 4 pi. My pi's cancel out. 180 divided by 4 is actually 45 degrees. So an angle of measure pi over 4 radians is equivalent to an angle of 45 degrees. So they are the same size, so they're on the same spot on our graph. So that's converting between radian and degree measure. So finding the length of arcs and finding the area of a sector. So let's look at finding the length of an arc, or arc length. So if I have a circle, then the distance all the way around my circle we call the circumference. And the way that we find the circumference is 2 pi r, where r is my radius. So we know what the r is the radius, but what is this 2 pi? So if you think of in radians, so this angle, this is in radians, and it will always need to be. So 2 pi radians, where's the 2 pi come from? Well, we said 180 degrees is equal to pi radians, and if you go back to our x and y axis here, if my initial side is on the positive x-axis, I go 180 degrees, there's pi, and I made half a circle. If I come all the way back around, so another 180, that's 360 degrees, which is 2 pi, right? Multiplying times 2. So I know 360 degrees is the same thing as 2 pi. So all the way around the circle, so the distance all the way around my circle is 360 degrees, but in radians that is 2 pi. So that's where the 2 pi in the circumference comes from. In section 1.1 we talked about or we looked briefly at what an intercepted arc was. So an intercepted arc, we said if we had a circle with the center and an angle that goes through it, then the piece that was in between the two sides of the angle is called our intercepted arc. And we can find the length of this thing. And so if you think about, instead of finding the distance all the way around the circle, I'm just finding this little distance right here. So the angle that I'm looking at now is no longer 2 pi, it's just the angle that's created right here. So arc length, we'll denote with an S for arc length. I think that's what your book uses. I don't know. But arc length, instead of 2 pi, it's just whatever our angle is. I'll call it alpha for right now, in radians times r, which is the radius. So alpha in arc length always must be in radians. So if it's not in radians, you need to convert it. But let's say in this case that alpha is equal to, the measure of alpha is equal to pi over 3. So that is in radians. How do I know? It doesn't have a degree sign. And r, let's say this is r, from here to here, is equal to 12 feet. Then my arc length, S, is equal to pi over 3 times 12. So 12 over 1 gives me 12 pi over 3, which is 4 pi, and our unit was feet. So 4 pi feet. Notice I didn't multiply this out. I simplified my fraction, multiplied that, but I kept pi inside of it. This type of answer is called either in terms of pi or an exact answer. So as you're working through the presentation problems, if you see something that says in terms of pi or an exact answer, they're meaning leave pi inside your answer. Simplify it as best you can, but leave pi. If we're looking for an approximate answer, then we'll actually plug this in our calculator and see what we get. But this is the arc length. I was already in radians, so I didn't have to convert, but if it is in degrees, you'll need to convert like we looked at just a few minutes ago, and then multiply it times the radius. So that is arc length. We can also find the area of this little section of our circle. That section we'll call the sector, a sector. So finding area of a sector. Again, very similar to area of a circle. So area of a sector. So a little refresher real quick. Come over to the side. Area of the entire circle is equal to pi r squared. Again, we know what the r is. R is the radius, but the pi. So in the circumference, we saw 2 pi all the way around the circle. This angle is half of that. So half of 2 pi is pi. And so this is the area of the entire circle. If I'm not wanting the area of the entire circle, though, I won't be looking at 2 pi anymore. So let's say I want the area of this sector. So I'm going to want half of the angle that's inside of there. So half of, let's say this is angle, again, I like alpha. So half of that angle alpha. So the area of this sector, this is r, is going to be 1/2 whatever the angle, again in radians, pi is radians in the regular area formula, so our angle inside of the area of the formula for the area of the circle must be in radians as well. So if it's not, you need to convert. So 1/2 alpha times our radius squared. So let's say that in this case, alpha is equal to we'll say 60 degrees, and we want to find the area of the sector. So we have our formula, but alpha must be in radians. We're given alpha in degrees, so I need to convert alpha into radians. So 60 degrees over 1 times, I'm going to radians, so I want the radians on top. So pi over 180. So I get 60 degrees times pi over 180 degrees. Degrees cancel out, zeros cancel out, 6 goes into 18 3 times, so this gives me pi over 3. So alpha is pi over 3 radians, and let's say our radius is 21 inches. So the area of this sector is 1/2 times pi over 3 times r squared. R is 21, so 21 squared. So I have 1/2 times pi over 3 times 441. So multiplying my fractions straight across, I get 1 times pi times 441 is pi 441 over 2 times 3 times 1 gives me 6. And cleaning this up a little bit, we kind of look at pi as a variable, so it's 441 pi over 6. Again, this is the exact value. If we're asked for an approximate value, then you just plug this in your calculator and get the approximate value. Our units for our radius was inches. This is area, so it must be inches squared, and this is the exact area of our sector. Okay, if you have questions, please feel free to reach out to me. Be working on the presentation problems, and I will see you on Monday.